I'm going to use this heat problem set, do a couple examples off of it to reteach how to do the problems on the heat quiz. Bear in mind that this is not the heat quiz, and these problems are not the ones that are on any of the heat quizzes, but the logic is the same. So when we learn to do this stuff, I'm going to write some formulas here. We had three formulas. We knew that we knew that the quantity of heat Q I'm going to change this around just a tad. Note the quantity of heat Q is equal to the mass multiplied by the heat capacity times the change in temperature, and that applies anytime there's a temperature change. So I'm going to put a graph right here. This axis is temperature. This axis is time. And I did this demonstration in class starting with ice. And with ice, we started at this flat line point. The temperature stayed the same until the ice melted. Then the temperature raised to the boiling point and continued to boil for a long time. And finally, we would have been able to raise the temperature of the steam were we able to catch it. In class, we only did from the beginning point. Let me show you again. So we started in class at this point, came across, raised the temperature, started to boil. In class, we never did get past here because I didn't collect the steam. But if I had collected the steam, it would have gone up to there. All right, so this formula applies, this Q equals mCp delta T formula applies anytime there's a temperature change. So right here, it also applies so once again, right here, it also applies right here and here, anywhere there's a temperature change. The second formula that we had was Q is equal to mass times heat of fusion. That formula applies right here. So anytime there is a melting or a freezing process, this formula applies, mass times heat of fusion. And then the third one and final formula, Q is equal to mass times heat of vaporization, that one applies right there. All right, so now we're going to go and work a couple problems that are associated with this graph and these formulas. So the first problem we'll look at is number 2 here. We have 25 grams of steam and it's cooling down to 25 from 125. So the energy change is the same whether you think of it as going from negative 25 to positive 125 or if you go from 125 to negative 25. Either way, the temperature of the heat change is the same. It's just that in this case, since we're cooling, the heat's released. If we were starting and warming up to 125, heat would be absorbed. So look at the graph first. I'll put a couple of marks here. Actually, I'll make a new graph. So right here, here's the graph. You remember at this temperature we had 0. Up here at the boiling point was 100. So negative 25 would be down here below 0. So down here. And positive 125 would be up here. Having some trouble controlling this little pin like I always do, but it's worse today. So this is negative 25 down here. And it's positive 125 up here. So what we really have to think about is how much energy does it take to get from this low point to this high point. So we're going to go up, we're going to go over. So from here, then over, then up, then over, then up. So we got 5 whole steps. So for the first step, we'll call this part A. In part A, we know that Q is equal to mCp delta T. We would know that because there's a temperature change, and that's the formula that applies when there's a temperature change. So we plug in our mass, which is what, 25 grams. The specific heat capacity, since we're in the solid phase, we'd use ice. It's 0.5 calories per gram degree C. And our change in temperature is from negative 25 up to this where the flat line occurs. What was the temperature at the flat line again? It was 0. So we're going to go from negative 25 up to 0, so the temperature change is 25 degrees C. All right, so I'm going to wait to work out the math. The second step will be to cross this line. We'll call that part B. So in part B, that was A, here's B, we have Q is equal to mass times heat of fusion. You're going to use the formula that applies to heat of fusion. Remember up here we talked about that. So the mass is still 25 grams, that doesn't change, and the heat of fusion is listed up here as 80 calories per gram. So times 80 calories per gram. We'll work it out in a few minutes. All right, up here, C, part C, we would use the formula that involves temperature change. So Q is equal to mCp delta T. Mass is still 25 grams. The specific heat capacity is 1 calorie per gram degree C. Come up here, you can see that, oh, can't see because it's too far. 1 calorie per gram degree C. And then the change in temperature, we're going from 0 up to 100. So how far is it from 0 to 100? Remember, we're trying to get all the way up to this top line, top temperature, which is more than 100. So how far is it from 0 to 100? I'm thinking it's 100. So the change in temperature will work out, or the change in heat will work out in a minute. That was part C. Now we're ready for part D. Part D is the flat line. So part D was boiling. So Q equals mHV. So you'd have the same 25 grams that we've always had. The heat of vaporization, it tells us right here, is 540 calories per gram. And then the last step is part E. So in part E, we've got a temperature change again. So E would be mQ equals mCp delta T. So the mass would be 25 again, didn't change. The CP would be 0.5 because we're up in the steam range. And the change in temperature, now we were at 100 before. Remember, we're up here, it's 100 degrees. We're going up to 125. So how far is it from 100 to 125? That's 25 degrees. That's calories per gram degree C. All right. So to do all the math, I'll use a calculator. So we've got 25 times, I'm doing this on a calculator on the side, 25 times 0.5 times 25 equals 312.5. So that is 312.5. Then I've got 25 times 80, and 25 times 80 is 2,000. So we have 2,000 right here. And that's calories because everything else cancels. Up here I got 25 times 100, so I'm pretty sure that's just 2,500. 25 times 540 is a pretty big number. So 25 times 540 is 13,500. And then the last one, 25 times 0.5 times 25 is again 312.5. And that's up here is calories, and these of course are calories because calories cancel out. So now if we add those all together, I got 312.5 plus 1350, doing this on the side again, and I'm going to add to that 2,500. I'm going to add to that 2,000. I'm going to add to that 312.5. So let's do that. So 312. I'm going to do it one more time, make sure I got the right answer. So 312.5 plus 2,000 plus 2,500 plus 13. Oh, I think I wrote a number wrong down up here. 13,500 plus 312.5 equals. So I got 18,625. But this number right here should have an extra 0 on it. So let's move this over a little bit. It should be a 0 right in there. So that's 13,500 because 25 times 540. I wrote down the wrong number, or else I erased it with my pen glitch. Bottom line is that's the number of calories it takes to get from 0 to 100. So now the total energy change was over here, 18,625. That's your answer. All right, I'm kind of out of time to make this video, so I'm going to talk about the other problems real quick and then leave it with you guys to do the retake if you want to. All right, so here we go. This is the first one. There's your temperature changes. Where's 25 on this graph? Right here. Oops. So where's 25 would be right in here. And 125 would be up here. So how many steps would you have in this problem? You notice this problem had 5 steps, but this one will only have 3 steps. Because you're going to go from here up, over, up. Okay, if you look at this one, up, over, up, over, up. So where's negative 15? It's down here. And where's 25? It's up here. So how many steps will you have? 1, 2, 3. So that'll be a 3-stepper. So you have to think about how many steps are needed for each problem. Here, here's the same graph. Once again, what's this temperature? 0. What's this temperature? 100. So from 95, you're up here. You're up here. You're going to 125 up here. So up, over, up. 3 steps. This one, you're going to go from negative 110 down to negative 20. So you can go, when I did the previous problem, I went down from low to high, but you could have gone from high to low, and really technically you're going from high to low because energy is coming out. So we'll do this one from high to low. So you go up, this is your graph. You're starting up here above 100, so you're going to come down to 100, you come across, you go down to 0, you come across, and you go down to negative 20. So 110's up here somewhere, negative 20's down here. So you got 1, 2, 3, 4, 5 steps. But on this one, you're going from 25 to 75, so look at the graph. Like that. 25's here, 75's here, so how many steps is that? Just 1 step. Quantity of heat released is 500 grams of water cool to 45 from 125. So you look at your graph again. Up, over, up, over, up. 125 is up here. 45 is over here. So you're going to go down to 100, across, and then down to 45. The answers are all here, so you want to try a couple before you try the quiz and know if you're getting them right or not. Then do the quiz, and you'll be okay. And that's the end of this little heat problem review.